What are the space propulsion energy systems that can power cities, cars, and other technologies? Space propulsion systems are primarily designed for spacecraft and not typically suited for powering cities or ground-based technologies. However, there are several advanced space propulsion energy concepts that, with adaptation, could inspire or lead to revolutionary systems for powering cities, vehicles, and other technologies on Earth. Here's an overview of these space propulsion systems and how their underlying principles could translate to terrestrial applications. 1. Ion propulsion, electric propulsion. How it works: ion propulsion systems, used in spacecraft like NASA's Dawn mission, ionize a propellant, usually xenon, by stripping electrons from atoms, creating ions. These ions are then accelerated using electric fields to generate thrust. Application on Earth. Electric vehicles, EVs. The concept of ion propulsion highlights the importance of electric propulsion for efficiency. While ion thrusters are not powerful enough for terrestrial use, the technology could inform future battery electric vehicles that rely on high-efficiency electric motors. Electric grids, the advanced power systems needed to generate and store electricity for ion propulsion systems, could inspire improvements in terrestrial energy storage, e.g., batteries or supercapacitors, and grid stability technologies. 2. Nuclear thermal propulsion, NTP. How it works: NTP uses a nuclear reactor to heat a propellant, usually hydrogen, and expel it through a nozzle to create thrust. This system promises higher efficiency than chemical rockets for deep space missions. Application on Earth. Nuclear power for cities. The principle behind NTP could inspire compact, highly efficient small modular reactors, SMRs, or advanced nuclear reactors that provide a clean, reliable energy source for cities. Hydrogen vehicles. The NTP concept of using heated hydrogen could be adapted to more efficient hydrogen fuel cells or propulsion systems for cars and trucks. Green hydrogen, produced by renewable energy sources, is already gaining traction as a clean fuel. 3. Solar sails, photon propulsion. How it works: solar sails use the pressure of sunlight, photons, to slowly propel spacecraft through space. Over time, this system can build up significant velocity without the need for traditional fuel. Application on Earth. Solar power for cities and vehicles. Solar sails reinforce the potential of solar energy as a scalable, renewable power source. Photovoltaic panels, inspired by solar sail technology, could be used to generate electricity for cities and EVs. Light-based propulsion. The concept of using photon pressure could eventually inspire laser-based power transmission systems, where concentrated beams of light power vehicles or infrastructure remotely, similar to wireless electricity transmission. 4. Nuclear fusion propulsion. How it works: fusion propulsion, still in development, aims to use nuclear fusion reactions, the same process powering stars, to generate enormous amounts of energy and thrust. It promises unprecedented speeds for space travel with very little fuel. Application on Earth. Fusion power for cities. If harnessed, nuclear fusion could provide virtually limitless, clean energy with no long-lived radioactive waste. Fusion power plants could be a breakthrough solution for powering cities with zero emissions. Hydrogen fusion in vehicles. On a smaller scale, advanced hydrogen-based fusion reactors could one day power vehicles, providing an ultra-efficient and clean fuel source. Though it is far from being realized, research in this area continues. 5. Antimatter propulsion. How it works: antimatter propulsion works by annihilating matter with antimatter, releasing enormous energy, far more than nuclear fusion or fission, as the two materials collide. While this remains purely theoretical, it is the most energy-dense propulsion concept. Application on Earth. Energy storage breakthroughs. While direct use of antimatter is not feasible, the study of antimatter highlights the importance of energy density. This could lead to innovations in high-density energy storage systems for cities and vehicles, such as next-generation batteries or other advanced materials. 6. Plasma propulsion. How it works. Plasma propulsion uses superheated ionized gases, plasma, accelerated by magnetic or electric fields to produce thrust. Examples include the VASIM, Variable Specific Impulse Magnetoplasma rocket, which can continuously accelerate spacecraft over long distances. Application on Earth. Plasma energy systems. The principles of plasma physics could contribute to the development of plasma-based energy generation systems on Earth, such as plasma arc technology for waste-to-energy conversion or industrial applications like cutting and heating. Plasma engines for transportation. In the distant future, plasma propulsion technology could inspire the creation of high-efficiency plasma engines for aircraft or even surface vehicles. Although this is a far-fetched idea for now, plasma propulsion showcases the potential of ultra-efficient, high-velocity systems. 7. Electromagnetic propulsion, M-drive. How it works. The controversial M-drive concept theoretically generates thrust by bouncing microwaves within a cavity, without the need for propellant. While it's not widely accepted by the scientific community, if proven, it would offer propulsion without fuel. Application on Earth. Magnetic levitation and transport. The M-drive concept relates to technologies like maglev trains, which use electromagnetic forces for propulsion and could revolutionize ground transportation by reducing friction and enabling ultra-fast travel. Wireless power systems. Electromagnetic propulsion principles could inspire wireless power transfer systems, enabling contactless charging for electric vehicles or even powering cities using microwave or radio wave transmissions. 8. Chemical rockets, traditional combustion. How it works. Chemical rockets, such as those used by SpaceX's Falcon 9, rely on the combustion of fuel and oxidizers, like liquid oxygen and kerosene, to generate thrust. While effective in space, they produce significant greenhouse gases. Application on Earth. Clean combustion technologies. Although traditional chemical propulsion generates greenhouse gases, research in carbon-neutral synthetic fuels or biofuels could help adapt combustion engines for vehicles or industrial use with reduced emissions. 9. Beamed energy propulsion. How it works. Beamed energy propulsion systems use lasers or microwaves to deliver energy to a spacecraft, removing the need for onboard fuel. The spacecraft receives energy remotely and converts it into thrust. Application on Earth. Wireless power grids. This principle could be applied to wireless energy transmission for cities or vehicles. High-powered beams could deliver energy over long distances without the need for power lines, potentially powering electric vehicles while they drive. Drone and UAV powering. Beamed energy could also keep drones, unmanned aerial vehicles, UAVs, and even satellites powered indefinitely without requiring onboard batteries or fuel. Key considerations. While space propulsion systems are designed for the vacuum of space and deep space missions, the advanced energy and physics principles behind these technologies could inspire breakthroughs on Earth. The challenges are significant, particularly in scaling them down for terrestrial use or adapting them to Earth's atmosphere, but ongoing research into energy storage, nuclear power, and electromagnetics could make some of these futuristic concepts a reality. For now, practical clean energy technologies like solar, wind, and batteries remain the most viable for powering cities and vehicles, but the exploration of space propulsion systems opens the door to a future of ultra-efficient, high-energy solutions for Earth-based applications. What are the best space propulsion energy systems to power cars, aircraft, cities, and society? The best space propulsion-inspired energy systems that could potentially power cars, aircraft, cities, and society are those that maximize energy efficiency, scalability, and environmental sustainability. While space propulsion is not directly applicable to terrestrial technologies, some of its underlying principles and advanced energy concepts offer valuable insights. Here are some systems with potential. 1. Nuclear fusion energy systems. Application: fusion power plants, future fusion-powered vehicles. Overview: nuclear fusion, the process powering the sun, offers an energy-dense and virtually limitless power source. Research is advancing in fusion reactors like ITER, which aim to harness fusion reactions for clean, large-scale energy production without long-lived radioactive waste. Potential impact: fusion could provide consistent and emission-free power, supporting entire cities and industries. Compact fusion reactors could also power large ships, aircraft, and potentially ground vehicles in the distant future. 2. Hydrogen-based systems inspired by nuclear thermal propulsion, NTP. Application: hydrogen fuel cells for cars, trucks, ships, and even aircraft. Overview: nuclear thermal propulsion uses hydrogen as a propellant, heating it with a nuclear reactor to create thrust. While direct nuclear-powered engines are impractical for Earth, hydrogen as a fuel source is promising. Potential impact: hydrogen fuel cells generate electricity by combining hydrogen with oxygen, emitting only water. Hydrogen is especially promising for heavy-duty vehicles, long-haul trucks, trains, and even aircraft, where it could replace conventional fossil fuels with zero emissions. 3. Battery electric systems inspired by electric propulsion, ion and plasma engines. Application: electric vehicles, electric aircraft, and electric grid energy storage. Overview: electric propulsion for space, like ion and plasma engines, highlights the potential of electric energy to propel with high efficiency over time. On Earth, advances in battery technology are critical for electric vehicles, EVs, grid storage, and intermittent renewable sources like wind and solar. Potential impact: next-generation batteries, like solid-state, lithium-air, or metal-sulfur batteries, could provide lighter, safer, and more energy-dense options for powering cars and planes. Grid-scale storage would also support citywide renewable energy use. 4. Solar power systems inspired by solar sails. Application: distributed solar grids for cities, solar-powered vehicles, wireless power systems. Overview: solar sails use the pressure from sunlight to move spacecraft, showcasing the potential of capturing photon energy. On Earth, photovoltaic solar cells can efficiently convert sunlight into electricity for widespread use. Potential impact: solar panels are increasingly efficient, affordable, and adaptable for urban and remote areas. Combined with wireless power transfer or roadside solar stations, solar energy could power EVs, public transportation, and even urban infrastructure. 5. Beamed energy propulsion for wireless power transmission. Application: wireless power grids, contactless EV charging, power for remote facilities. Overview: beamed energy propulsion transfers power via laser or microwaves to spacecraft, removing the need for onboard fuel. On Earth, beamed energy could enable wireless power transmission across long distances. Potential impact: wireless power could enable roadside EV charging, keeping vehicles charged while in motion, and power remote or offshore facilities. It also offers potential for drones and aircraft, powering them without heavy batteries. 6. Nuclear small modular reactors, SMRs, inspired by space nuclear reactors. Application: small nuclear power plants for cities, industrial facilities, and military bases. Overview: space missions have explored compact nuclear reactors to power spacecraft. These SMRs could be adapted to generate reliable energy for cities or remote areas on Earth. Potential impact: SMRs are designed to be safer, scalable, and faster to deploy than traditional nuclear reactors. They could provide a zero-emission baseload energy source for cities, complementing intermittent renewables like wind and solar. 7. Magnetic levitation, maglev, and electromagnetic propulsion inspired by EM drives. Application: maglev trains, hyperloops, and high-speed rail networks. Overview: electromagnetic propulsion technology used in EM drives can inspire terrestrial maglev systems that reduce friction to achieve high speeds. Maglev trains use superconducting magnets to levitate and propel vehicles with minimal energy. Potential impact: maglev technology could enable ultra-fast, energy-efficient transportation systems for intercity and international travel, reducing reliance on traditional fuel-burning aircraft and cars. 8. Plasma-based waste-to-energy conversion systems inspired by plasma thrusters. Application: waste management, industrial energy generation, urban heat and power. Overview: plasma thrusters in space use superheated ionized gases for propulsion. On Earth, plasma arc technology can convert waste into energy by breaking down materials at high temperatures. Potential impact: plasma waste-to-energy systems could help cities manage waste while generating electricity and heat, providing a clean energy solution for urban centers. 9. Supercapacitors and advanced battery storage inspired by high-energy density propulsion systems. Application: rapid charging for EVs, urban energy storage, portable power sources. Overview: space propulsion systems rely on advanced energy storage to maximize efficiency and minimize weight. Supercapacitors and advanced batteries could offer rapid, high-density energy storage for terrestrial use. Potential impact: supercapacitors allow ultra-fast charging, perfect for high-demand, high-turnover applications like buses, emergency vehicles, and high-speed trains. For city grids, they offer a robust way to balance renewable energy and demand. 10. Antimatter research for high-density energy storage. Application: theoretical next-gen energy storage for large-scale and remote applications. Overview: antimatter propulsion explores reactions between matter and antimatter to generate enormous amounts of energy. Though currently impractical, this research emphasizes ultra-high-density energy. Potential impact: innovations from antimatter research could inspire advanced materials and methods for energy storage, particularly for portable power in challenging environments or for long-duration battery storage. Summary: towards a sustainable and high-energy society. The fusion of space propulsion concepts and ground-based needs creates exciting possibilities for clean energy and efficient power systems. The most impactful systems will likely combine multiple technologies to meet diverse energy needs. Fusion, SMRs, and hydrogen for large-scale, stable power generation. Battery, supercapacitors, and wireless charging for vehicles and localized energy needs. Solar, maglev, and plasma-based waste-to-energy to create resilient, sustainable urban infrastructure. Space propulsion inspires these high-density, clean energy systems that could power cars, aircraft, cities, and society, bridging the gap between space exploration and Earth's sustainable energy future.